In this session, we're going to discuss torsion, specifically torsion on shafts with circular cross-section, solid circular cross-sections. Torsion can be a complicated problem, but in this particular case of shafts with circular cross-section, the mathematical formulation is relatively easy to formulate and to understand. So I'm just going to present here some of the basic formulas. I'm not going to derive them. You can find those in many textbooks. The first one is that as you apply a torque, a torsional moment, which is basically a moment that is going around the axis of the member, right? Let's say on a member like this, right, you apply torsion. It's a moment that's rotating around the axis of the member. If you apply a torque in that direction, these points, let's say, for example, point A, which would be up here if the shaft is undeformed, once you apply torsion to it, that point will move radially from A to A prime, making an angle with respect to the original position. And that angle can be found by multiplying the magnitude of the torsional moment times the length of the shaft divided by the shear modulus of the material and divided by the polar moment of inertia of the circular cross-section. A relatively easy formula. It's analogous to the formula that we use for deformations due to axial loads, where we had PL over AE. In this case, instead of P, we have torsion. L remains the same. Instead of area, we have polar moment of inertia. And instead of elastic modulus, we have the shear modulus. So that takes care of the angle. How much does this shaft rotate elastically as a function of the applied torsional moment? You can see that that relationship is linear. The other important result is that the stress at any point located at a distance r from the center of the shaft, the stress is going to be the torsional moment times the distance from the center of that point divided by the polar moment of inertia, which is given by the integral of r squared dA, which for circular cross-sections comes out to be pi diameter to the fourth divided by 32. So these are basically the two fundamental essential formulas for torsions in circular shafts. I'm going to just solve a simple problem here that would sort of illustrate how you use these formulas. Say we have a shaft here of circular cross-section, and it has a rigid arm, sticks out this way like that. This is fixed at one end, and we have a load applied to it, 1 kip, and the eccentricity of that load, the distance from the line of action of the force to the center of the shaft, is 6 inches. The length of the shaft is 16 inches, and the diameter is 2 inches. But we wish to find out what will be the rotation of this rigid arm as the load creates a torque on the member. For this example, this arm, as I said, is rigid, so it just basically rotates as the shaft deforms in torsion. In this case, the polar moment of inertia, as we mentioned before, is pi diameter to the fourth divided by 32. and that equals 1.5708 inches to the fourth. The torsional moment is 1 kip times 6 inches, so that's 6 kip inches. And as we mentioned, the diameter is 2 inches. If we use this formula to compute the maximum shear stress, which will occur, right, at all these points along the circumference of the cross section of the shaft, right? The maximum stress will occur on points which are farthest away from the center. In this case, the maximum stress would be 6 kip inches times the radius, which is 1 inch, divided by 1.5708 inches to the fourth. And if you look at the units, the answer comes out as it should be in kips per inches square, or KSI. If you compare this number to, let's say that this shaft is made out of steel, and in that case, the steel has a maximum shear capacity of approximately 21.75 KSI, which is about 75% of its tensile stress capacity, which would be about 36 KSI. So this stress is well under the capacity of the steel. In this case, shear capacity would be 21.75 KSI for mile steel. So we are okay in terms of demand and capacity. Now, if we wish to find the rotation angle of the rigid arm, we have to apply this formula. And if we do that, we find that the rotation angle is going to be 6 kip inches times the length, which is 16 inches, divided by G, which is the shear modulus of steel. The shear modulus of steel is approximately 11,500 KSI. So put that in here, 11,500 KSI. And the polar moment of inertia of the circular cross-section, which is 1.5708 inches to the fourth. The angle comes to approximately 0.0053 radians. Again, this formula is in radians, in case I forgot to mention that, which, if you take it to degrees, becomes approximately 0.3 degrees of rotation. So basically, this is how you compute shear stresses and rotation angles in elastic circular shafts. These are very popular in many engineering applications, rotating machinery, and other kinds of structures. So these formulas really come in handy quite a bit. Also notice that, check the units here, you get you basically come out in units of radians, because all the kips and inches cancel out, and here you get KSI. So it all works out nicely. So this is the formula for rotation angle, and this is the formula for shear stress. Now, let's suppose you wanted to calculate the angle halfway through the length. In that case, instead of putting in L, right, you would put in L over 2, because you don't want the angle at the end, you want the angle halfway there, right? Or at whatever distance you wish to compute that angle. The other thing is that this assumes that the shaft is subjected to a constant torsional moment. If you have a torsional moment that is varying across the length for whatever reason, then this formula needs to be modified to include that effect, and we will discuss that on future sessions.